Hello and welcome. Today we're going to look at a question involving trigonometric identities and complex numbers. In this case, we are asked to prove that the left-hand side of this equation here equals to the right-hand side of this equation. Now, at first glance, this question looks rather complicated. And if you're not sure where to start for this kind of question, you should always try to look for the hints within the question. In this case, we can observe that over here, we have 1 plus cos alpha plus sine alpha to the power of k. And over here, we have similar form, but instead we have a minus I sine alpha with the same power of k as well. And on the right side, we notice that there's a term called cos half k alpha. So over here, we can see that the power of the k actually came down to be a part of the trigonometric function here. And this looks suspiciously similar to the Moivre's theorem. Now, just a quick review on Moivre's theorem over here. If we are given cos theta plus I sine theta to the power of k, and we remember that cos theta plus I sine theta can be rewritten into exponential form as e to the power I theta, and of course the power of k will still remain the same. By the law of indices, the power here can be multiplied inside, and that gives us e to the power I k theta. But let's not forget that this exponential form of the complex number can be rewritten into trigonometric form so that it gives us cos k theta plus I sine k theta. So in other words, the Moivre's theorem here tells us that you can rewrite this form of the complex number into this form, where you can clearly see that the power of k can be brought down into the trigonometric term. And that is very similar to what we have over here. But even so, we still cannot start with just the Moivre's theorem alone. Because if you look at the question here, the real term of the complex number here involves 1 plus cos alpha. So there's a redundant term of 1 here if we want to apply the Moivre's theorem. But now we notice there is another hint where we can see that on the left-hand side of the equation here, the trigonometric term always involves alpha. But on the right-hand side of the equation here, it involves half k alpha and half alpha. Now, whenever we see this, this is a sign that most likely we are going to need to use the double angle identities, which is something over here. Here we can see sine 2a equals to 2 sine a cos a, and cos 2a can be written as cos square a minus sine square a, but it can also be written as 2 cos square a minus 1 and 1 minus 2 sine square a. With both the information here, I believe we can start the question. Over here, I know that if I want to apply the Moivre's theorem, I need to remove the 1. But to remove this term of 1 over here, we most likely will require the double angle identities. Therefore, let us start by applying the double angle identities onto the left side of the equation first. For the sine alpha, we don't really have any choice. We can only make use of this identity here to write our sine alpha as 2 sine half alpha cos half alpha. But what about cos alpha here? Now for cos alpha, we have 3 options here. If you are not too sure which identities to use, then you can just do trial and errors. And that is the part of the learning process in mathematics. You should never be afraid of making any mistakes. Especially if you are a beginner, then you should try everything that you can think of. And whenever you make a mistake, then you will know what not to do in the future. And as you build up more and more experience in solving these mathematical questions, you will naturally build up a certain intuition as to what kind of mathematical equations or operations or identities to use in different kinds of questions. In my case, I'm going to expedite this process by utilizing my experience and say that most likely we are going to need to use this identity here. Now, there are 2 reasons why I picked this identity. The first reason is because if I look at the right-hand side of the equation, there is a common factor of 2 to the power k plus 1. So from there, I can tell I will most likely need a factor of 2 in my identity. Now that of course gives us 2 possibilities here, either 2 cos square a minus 1 or 1 minus 2 sine square a. But let's not forget that we still want to remove the redundant term of the 1 over here. So by using this identity, the negative 1 here is just right to be used to remove the term 1 over here. So now let's substitute all our identities over here into the equation on the left hand side. And we will get this. We now simplify the equation by seeing that 1 minus 1 will give us 0. The same thing on the second term here, 1 minus 1 will be 0. And that will give us this form of equation. Now, before we continue any further, I think it's a very good idea that we try to factor out some of the common factors here. Now, we can see that for every single term, there's a common factor of 2. And not only that, there's also a common back factor of cos half alpha. So for both brackets over here, let us try to factor out 2 cos half alpha so that we can get something like this, where we can further put the power into every single bracket, and we can finally get something like this. Now this gives us a very convenient form because we notice that this term over here and this term over here can be simplified using the de Moivre's theorem, which can now be rewritten into this form. So notice that I have applied the de Moivre's theorem from this form into this form over here, and also from this form into this form over here. And from here onwards, the rest are just simple mathematics. We can see that 2 cos half alpha to the power of k is a common factor between these two terms, which we can factor them out. And the remaining terms can be combined together, and finally we will get something like this. Here we can see I have pushed the power of k into each of the term, which gives us 2 to the power of k times cos power k half alpha. And then the remaining terms are combined together. Now over here we can see that here we have a I sine half k alpha and a negative I sine half k alpha. So these two together will give us 0. And cos half k alpha plus cos half k alpha will just give us 2 cos half k alpha, which will be something like this. Now if we compare the form that we have over here with the given right side of the equation, so cos to the power of k half alpha, cos power k half alpha, cos half k alpha, cos half k alpha. So the only difference here is they have 2 to the power of k plus 1, whereas we over here we have 2 to the power of k multiplied by 2. But that part is simple because 2 to the power of k multiplied by 2 is the same thing as 2 to the power of k multiplied by 2 to the power of 1. And by using the law of indices, we can combine them together and get 2 to the power of k plus 1. Which means that we can finally rewrite this into this form, which is exactly the same as the given equation on the right hand side. And that is it.